I'm going to start by saying I'm sorry, but this is actually about a research project joined with all of these lovely people. But don't worry too much. There will be one joke, one insane plot twist, and maybe some things for your bingo card. So please stay with me for now. Curves you can trust. Notwithstanding the recent total annihilation of psych, we, the people, are still on the quest for a curve you can trust, which means that, well, one thing you can use to attack a lot of isogeny-based schemes is known endomorphisms. I've applied some color coding here. Red means it's bad. So color coding, red, known endomorphisms are bad. Well, you know, the obvious solution to this is you just get rid of the known endomorphisms. You apply unknown endomorphisms, which are green, so that's good. So that's easy, problem solved. Thanks for listening, bye. Well, but that's not gonna happen because, well, okay, let me first say one more thing. We label this as supersingular elliptic curve of unknown endomorphism ring because that's what it is. And if you take the first few letters of each word here, you get an acronym. It's called a SECURE. And if there's anybody in the audience who's British, the spelling is secure. This is the one joke, I'm sorry. It's actually also stolen from Luca De Feo, Captain Luca De Feo, I must say. So I wish I had made it up on my own, but I didn't. Right, so as I kind of said before I talked about the joke here, we don't really know how to construct such a curve. So this is where we as a community are really just kind of scratching our heads. There is kind of a folklore solution to this, which is that random curves have unknown endomorphisms, again, color-coded green to show that it's good. But we don't really know how to construct a random elliptic curve, a random supersingular elliptic curve. The only way we know how to do this is by using random walks, but then you kind of know a path from a curve that has known endomorphisms to your new curve, and that transports the known endomorphisms, so that doesn't work. You can still do this and just reveal the endpoint of your random walk, but then of course the person who does this thing has a backdoor to the entire thing, so you need some kind of trusted setup. And whenever we have this, as cryptographers, what we want to do is a distributed trusted setup. So we kind of basically chain secret random walks generated by different people, and then we kind of have to make sure that everybody does this properly, and at the end, the final endpoint of the entire thing will be our new random elliptic curve. So this is what it looks like. You have one special starting curve. It can have known endomorphisms, red, bad. And then you just kind of randomly walk around. You get up, you know, Alice can do this. She ends up at a new curve, and then she passes that on to Bob. Bob will also do a random walk, ends up in a new curve, reveals that that's the endpoint, that's the random curve. We're going to use this. This is our trusted curve. Of course, we have to make sure that they don't cheat. So what you need here is a proof of isogeny knowledge, proof that between two publicly known elliptic curves, you know a secret isogeny. So what we have is a proof of isogeny knowledge for supersingular elliptic curves over pretty much any base field. It's statistically zero knowledge, which relies on some very non-obvious properties of isogeny graphs. So there's a lot of deep math in here. It's computationally sound, assuming nothing but the pure isogeny problem. So, you know, if you're still thinking about psych, it's not the psych problem. So this is still possibly secure as far as we know. And indeed, we're actually planning to kind of run a trusted setup ceremony in reality to get some supersingular elliptic curves with this property. Our intended application for this was to defend SIDH and psych in depth, because it's not really vulnerable to this, but it could help for some attacks. Unfortunately, psych recently passed away due to these 3 attack papers, so that's not going to happen anymore. If anybody has new applications in mind, please talk to us. We have plenty of time to do this, but so far we're not really sure who needs this. I'm going to say that we're still using the technical tool of SIDH squares, but you know, the marketing isn't really that exciting anymore. So we're kind of just turning this around by 45 degrees. And so, you know, this still looks like a square, but if we just call it isogeny diamond instead, it sounds so much better and it looks really tough. So this is what it is now. Thanks for listening.
Hello, I'm back. Don't worry, there are no shell scripts this time. All right, so we've seen some spectacular complete breaks of various post-quantum candidates. We saw Rainbow is broken in a weekend on a laptop. Psych is broken in hours or even minutes. And we're excited to present some further work in laptop-based cryptanalysis. These are very exciting times to be a cryptanalyst with a laptop. This time we're attacking an older but still used in legacy systems block cipher, or rather such a block cipher that is iterated 3 times. That's right. Triple rot 13 is broken in 3 seconds on a laptop. And this is joint work with Peter Schmidt-Nielsen. All right, so we all know the story of triple rot 13. Single rot 13 was a sound design, but its 0-bit key size was just too small to prevent brute forcing. Double rot 13 was proposed. Excuse me? Double rot 13 was proposed, but it turns out to be vulnerable to a meet in the middle attack. Thus, triple rot 13, which provides twice as many bits of security as single rot 13, namely still 0. So how does rot 13 actually work? Now, normally it's presented using weird non-standard mod 26 arithmetic, but there's actually a much cleaner description of it. It's actually just a standard Feistel cipher. It has 8-bit blocks, 0-bit key size. There are 6 Feistel rounds in a single rot. Each of them is just a 4-bit S box. You iterate 13 times for rot 13. We were actually able to, with the help of a SAT solver, reverse engineer the S boxes in rot 13. And I will say this took significantly more than 6 seconds on a laptop. It is surprising that this is possible, given that the number of permutations of 8 bits, or 7, because rot 13 is not actually specified on non-ASCII characters. The number of such permutations is far larger than what you can do with 6 4-bit block ciphers. There's 4-bit S boxes. So this is a little surprising that this works for all except braces, brackets, pipe, backslash, tilde, and caret. But this actually does work. So I'd like to draw your attention to these S boxes because they look a little strange, and we actually have some concerns that they might have been maliciously selected based on their sparsity and their low algebraic degree. We also noticed a number of non-ideal properties. Most notably, we found a differential characteristic that holds with probability 1 through not just all 6 Feistel rounds in rot, or through all 72, 78 Feistel rounds of rot 13, but actually through all 234 Feistel rounds in triple rot 13, which is extremely non-ideal block cipher behavior. I don't have a slide for it, but using a SAT solver, we were actually able to solve for the plain text that goes to a given triple rot 13 ciphertext to completely break in mere seconds triple rot 13 on a laptop. So again, I'll ask you to use your imagination because PDFs only give arbitrary code execution when you don't want them to. And there we have it. In 3 seconds, we have broken triple rot 13. I will say before you ask, yes, this is triple rot 13 in ECB mode, as you can probably tell. This is, believe it or not, still the most common mode of operation for triple rot 13 in practice, even though we all know that triple rot 13 GCM over a 2 to the 8 size Galois field would be much better, or even just triple rot 13 CBC. Where do we go from here? Well, triple rot 13 is dead, so clearly we all need to come together to form an advanced rotation standard that we can replace it with. I would like to propose the alternative solution that we destroy all laptops. Thank you.
Test. Neat. Okay. Do I do the clicky thing? I do the clicky thing by pressing the space, right? That's an affirmative. Cool. All right. There's a clicker. There's a clicker. Oh, that does look clicky. Hello, I'm Thor. And I wanted to talk to you about a thing that happened last week, which is that on Monday of last week, by tweet, the Department of the Treasury announced that sanctions were imposed on the application Tornado Cash. And I wanted to sort of talk about what exactly happened and why it should matter to people in this room. So yeah, let's kick off. So what is the context? So Tornado Cash is a cryptographic protocol, a non-custodial mixer deployed on Ethereum. So what that means is that if a user deposits funds into Tornado Cash as an application, they can specify an address that they would like to withdraw them out of, but it's not transparent to any sort of statistical analysis what the input led to as an output if the user is doing it correctly. So there's some legal precedent about non-custodial applications and code in general. So in 1999, as a sort of like result of the crypto wars, so-called crypto wars of the 90s, source code is protected under the First Amendment. That means that if a developer produces some code, that code is not illegal, it is protected. And second, there was some recent guidance by FinCEN, which is a department at the Department of the Treasury of the United States, that said that custodial service providers are subject to the Bank Secrecy Act, and that non-custodial software providers are not subject to that. What that specifically means is that, am I speaking quietly? Sorry. So yeah, what that specifically means is that if you are a application that takes custody of assets and there is an administrator of such assets, you are a custodial service provider. Tornado Cash is not a custodial service provider. So all prior sanctions and arrests have been of custodial service providers, which is in alignment with the FinCEN guidance. Tornado Cash is not a custodial service provider, and this should be sort of alarming for a couple of reasons. So what happened? On August 8th, which is last Monday, the US Treasury sanctioned Tornado Cash. And what this means is that all of the funds that were in Tornado Cash are inherently burned, because that means that anyone who wants to use such funds would be violating US sanctions law. And what that also means is that if you sent a transaction from Tornado Cash to, say, Brian Armstrong, the CEO of Coinbase, Brian Armstrong would be in violation of US sanctions law if he was to use all of the funds in his wallet, and this has happened. He hasn't actually sent a transaction, but people have sent funds from like Tornado Cash to like various prominent addresses to say like, hey, so now you are in violation of sanctions law if you use all the money in your wallet. So that's a thing. So subsequently, USDC, the second largest stablecoin, moved to block all Tornado Cash users' addresses. And since this is cryptocurrency world, they can programmatically do that so that if you use cryptocurrency, Tornado Cash, from Tornado Cash, the USDC contract will automatically block you. And that means that you are inherently blocked from using the second largest stablecoin on cryptocurrency world, which is kind of disturbing. Subsequently, GitHub did platform the Tornado Cash repo, and on August 12th, that is Friday, the Tornado Cash developer was arrested in Amsterdam for the stated reason that they were suspected of being a Tornado Cash developer. Suspected of. And that's kind of disturbing because that means that a developer of a cryptographic protocol was arrested for developing a cryptographic protocol. So what does this mean for all of us? Well, we as developers of cryptographic protocols are all sort of subject to the similar assumptions of the Tornado Cash developer. Thank you for my talk. Here's some information about the arrest, if you would like to read more. That's my talk. Thank you.
Hello? Okay. Oh, yeah, that would be really nice. Even have slides. Hi, so I'm John Kelsey. I work at NIST. I'm also a PhD student at K Leuven that I'm taking forever on. Sorry, Bart. And this is joint work with Stefan Lukes and Natalie Lang at Bauhaus University in Weimar. It's about threshold hash-based signatures. So first thing is, what's a stateful hash-based signature? Because that's what I'm going to be talking about. So there's this really old work from like the late 70s, early 80s, about building one-time signature out of hash functions. The idea is if you have a hash function, you can use this to construct a signature scheme with a public key and a private key, works just like you'd expect, except you can only sign once with each private key, or you'll have a, or you'll lose all your security. So you wouldn't think this would be very useful, but it actually turns out to be, because you can put them in a Merkle tree. Let me see if I can actually use a laser. Nope, apparently not. Oh, I can, wow. So you can put them in a Merkle tree and build, like, generate 2 to the 16 of these things, build a Merkle tree, use the root of the Merkle tree as effectively your public key for the composite key. And then anytime you want to sign, you choose a one-time signature you've never used before. Very important that you've never used it before. You sign the message, and then you also include, along with the one-time signature, the Merkle tree path. And that gives you a useful scheme. You can actually do this to solve real problems. Sorry, I'm not sure if you can hear me. So the big thing to understand about this, the big security issue is you could sign 2 things with the same key. And if you do that, then you're just doomed. So what we do in this paper is we start with any kind of stateful hash-based signature scheme, and we use it to construct a threshold hash-based signature scheme. So a threshold signature. So all the normal properties, you take your private key, you split it into shares. Let's say you make 6 shares and you make a 3 out of 6 threshold signature scheme. Now, any 3 of your trustees can sign a message, but any 2 of your trustees who are compromised can't sign a message, can't learn any private keys, can't do anything. Okay. Threshold signatures are super useful. They actually be much more widely used than they are. They're very useful both for security, right? Because you can have a device compromised and still survive. And they're also very useful for redundancy. So if a device gets dropped off a cliff or something, you can still keep signing. So some details of our scheme that aren't super important. We can support reasonable size parameters like 3 of 5 or 3 of 6 signatures or 6 of 6 signatures. If you want 50 of 100 signatures, you can't do it with our scheme. It's just not practical. You could do it, it would just be horrible. We need a big shared public string, and it'd be about 2 gigabytes for 2 to the 16 signatures. And in the paper, we show some ways that you can get around that, the ways that you can use that. You could just use a cloud service provider. We provide in our paper protocols involving an untrusted helper whose only job is to manage the public string, and who doesn't have the power to forge signatures, do anything bad to you, can't even censor signatures. All he can do is just deny service. Other than that constraint, we have extremely good performance. It's symmetric crypto only, point-to-point communications, no broadcast channel or anything horrible like that. Computationally very cheap. The trustees don't need a lot of memory, so it's actually quite practical. In terms of security, we have a reduction proof. We reduce our security of our scheme to the security of the underlying hash-based signature scheme, and then also the security of our PRF. So like if you can distinguish the PRF from a random function or forge signatures, those are in our bound. The full paper is on ePrint. I will just say one thing, why should you care? The main reason you should care is there are a lot of uses of hash-based signatures in the world where it would just be a lot nicer to have a threshold signature. So you can actually get this redundancy property and also the security property. Okay. These techniques are very practical. They can be implemented now. Stefan has a couple of students working on an implementation, so hopefully we'll have some code up eventually. And you today, well, after you read the paper. And this also gives you a defense against the big problem with stateful hash-based signatures, right? The big problem with stateful hash-based signatures is you could reuse that key. Remember, you have this job of I have to use a key I've never used before to sign. If you screw that up, which is really easy to do in your implementation, then you reuse a key and it's a disaster and people can forge your signatures. So in this case, if you use like say a 3 of 5 signature scheme, all 3 trustees have to agree on the key to use, on which one-time key to use. So only if all 3 trustees agree to reuse a key, will you ever reuse a key. So this protects you against almost any way that you could do this accidentally, right? So if 3 trustees want to screw you over, they can, but they already can because it's a 3 of 6 threshold scheme. So that's it. Please check out our paper on ePrint. We'll eventually publish it somewhere, but I think this is really useful. We haven't filed any patents on it and aren't planning to. I can't promise that nobody else has ever done it. But please look into this because I think it's useful and be cool. All right, that's it. Thanks.
So for my main program talk yesterday, I did something weird, which is talk about wormholes. So for the rump session talk today, I'm also going to do something weird, which is give a typical boring talk. Okay, so this talk is happening thanks to my co-author Zvika Brekersky and Ron Kennedy. And I will be talking about computational hardness needed for quantum cryptography. Thank you. So EF5, this is the quantum hardness that we consider. What is it? Well, it is let's first think of what it is classically. So classically, it's basically just two distributions generated efficiently by two BPP algorithms. And they satisfy two additional properties called statistical farness, which is saying that these two distributions are statistically far, and computational indistinguishability, which says that these two distributions are computationally indistinguishable. And it is a classical result by Goldreich, which shows that classically this kind of object is equivalent to one-way functions, and therefore it is also equivalent to commitments. And by the way, this EFI name is tentative. If you hate it as much as I do, feel free to suggest a new name to me. But it turns out that there is this work by Yan, which shows that actually quantumly, you can directly go to statistically binding commitments from this EFI and backwards. So the catch is that by the work that I talked about yesterday with Prabhanjan Anand and Henry Yuan, and also the concurrent work by Morimi and Yamakawa also happened yesterday. We know that quantumly EFI cannot give you one-way functions. So somehow the work of Yan is able to get around this without even ever talking about one-way functions. Okay, so what did we do? Well, we basically showed that we basically extended this equivalence to other objects. So it is known if you have a VFI, you can get commitments, OT, MPC with some statistical security. And then we observe that this suffices for QCZK for QMA with only one copy of the witness. Also, you can prove all of QIP in QCZK. On the other hand, we also showed that very weak forms of commitments, OT, MPC, or QCZK also imply EFI. These include like, they don't satisfy any statistical security. They only give you, they only have semi-honest security. And even, you can even consider objects like 2PC with very weak but still non-trivial functionality, or QCZK for non-trivial languages. And along this line of thoughts, we also get an auxiliary result showing that quantum computational zero knowledge is unconditionally equal honest verifier QCZK. So that's it. Thank you.
Here's your quick. I got it right here.
Thank you.
No, my beer.
Test.
Thank you. Yes, this is a song, but we don't need no stinking external audio if you all help, and you'll know what to do.
That's right. Audience participation. All right. We ready?
Ready.
All right. Well, we're back at UCSB after a long absence. Josh, good to be back here.
Great.
There do seem to be an inordinately large number of papers at crypto this year.
Yes, indeed, Brian. There are nearly 100 papers of crypto this year.
Nearly 100. That's a lot. Do you know the exact number?
Well, in fact, there were 93 regular papers in the program, if you look there, and 3 best papers. That brings us up to 96. But 3 of the regular papers in the program were actually soft mergers. So there were 2 papers sharing each of those slots. So there's an additional 3. So that gives us a total of
99 papers at crypto this year. 99 papers this year. I found a flaw.
Time to withdraw.
98 papers at crypto this year. Come on, everyone sing the center.
papers at
98
crypto
papers at crypto this year.
98
98 papers this year.
Looks like mine.
We should combine 97 papers at crypto this year. 97 papers at crypto this year. 97 papers this year. What about psych?
What's not to like? Oh.
96 papers at crypto this year. 96 papers at crypto this year. 96 papers this year.
No vaccine card?
From crypto, you're barred. 95 papers at crypto this year. 95 papers at crypto this year. 95 papers this year. Drink wine from Napa.
At Kappa.
94 papers at crypto this year. 94 papers at crypto this year. 94 papers this year.
Your visa's delayed?
It's all a charade.
93 papers at crypto this year. 93 papers at crypto this year. 93 papers this year.
Eat too much shrimp.
And feel like a blimp.
92 papers at crypto this year. 92 papers at crypto this year. 92 papers this year.
Apply induction.
To what has been sung. 6 papers at crypto this year. 6 papers at crypto this year. 6 papers this year. But Yuval is late.
And crypto can't wait.
No papers at crypto this year. No papers at crypto this year. No papers this year.
Sit on the beach
Then go home and teach.
and
Submit more papers to crypto next year.
We'll give you until 10:10. Go get more beer.